Hello, welcome to a talk on special theory relativity for beginners. My name is Sangam Banerjee and my details are given below. So the plan of the talk will be, I will talk about inertial frame of reference, time dilation, length contraction, simultaneity, causality, velocity addition, then Einstein's E is equal to mc square famous paper, then Lorentz transformation, then world line, then four vectors. This is your position 4 vector, velocity 4 vector, momentum 4 vector, acceleration 4 vector and force 4 vectors. And then hyperbolic polar coordinates, then Rindler's accelerated frame, Rindler's horizon, and then we will summarize. So in the special theory relativity, Albert Einstein introduced two main fundamental assumptions that form the basis of the theory. These assumptions are principle of relativity, that is, the law of physics are same in all inertial frame of reference. In other words, the outcome of all physical experiments are consistent regardless of the motion of the observer. So this, as we proceed in the lecture, you will understand what it means. So an inertial frame of reference is one in which the motion of a particle not subjected to forces is in a straight line and at constant speed. And the second assumption is constancy of the speed of light. The speed of light in a vacuum, denoted by c, is the same for all observers regardless of their relative motion or motion of the source of light, which means that at all inertial frame, whether at whatever speed the observer moves, the velocity of light remains constant. So now we start with time dilation in special theory relativity. Here I show a figure and the man is in a stationary frame. Here is standing on the floor and shining a light towards the ceiling, and the distance between the floor and ceiling is L0. So and the light bounces back, so the distance traveled by the light is 2L0, and we know that 2L0 by the time taken will be the velocity of the light. So this we have studied in school. Now suppose this frame is moving and the man is standing here in a stationary, and this man shines the light, and the stationary man will see this mirror which is there will move because this is now in a moving frame, this S prime I'm calling it, and the light, this mirror will move here, so this light has to go here, and then the floor will also move and the light will bounce back here. So he sees a light, it is tilted, and he measures the distance traveled is c delta t by 2. Very similarly here, this delta t prime is the time taken in the moving frame. Okay, so I will be, whenever there is a prime, it is moving, and this vessel is moving with velocity v, so I write v times delta t prime by 2 because this is the time taken for the vessel to move here. So if I use a simple Pythagoras theorem, that is this hypotenuse, so this is your base and height, so I write that this square plus this square here I have written, and L0 is nothing but, I know L0 is c delta t by 2. From here I get it, and I substitute it here in this one, and then if I rearrange it, c gets cancelled here, this c, this is v by c, so I can rearrange it like this, and then delta t prime I take it to the left hand side, so this is delta t prime square 1 times this is your v by c the whole square, this is v square by c square is equal to delta, and this 2 will get cancelled in the denominator, all have the same 2. So we can write this delta t prime, if I take a square root and I bring this to the denominator, I'll get delta t by square root of 1 minus v square by c square, that I can write this 1 by square root of 1 minus v square as gamma, and delta t is the time in the rest frame and delta t prime is the time taken in the moving frame, and this factor is called the Lorentz factor gamma, and since v is always less than c, so this will be 1 minus some small real number, so this is less than 1, so 1 divided by some number which is less than 1 will be greater than 1, so here that's why I have written it, since v is less than c, gamma is greater than 1. So since gamma is greater than 1, this gamma is greater than 1, so delta t prime by delta t will be greater than 1, so since this is greater than 1, delta t prime will be greater than delta t. So this man measures this delta t prime to be greater than delta t, that is dilated. So one can say that moving clock, a clock in S prime frame, runs slower than the clock in S prime. So he measures this clock is running slower than his clock because this delta t prime is greater than delta t. Okay, now we discuss length contraction. So now this man is standing inside this vessel or a container, whatever it is, and is standing still and shines a light, and the length of this container is say L0, and so light traverse is twice L0, and we know that velocity, this is velocity of light, that is distance traveled per unit time, so this is your delta t, this is velocity, and when I say delta t, that is, suppose he has a stopwatch and he starts a time and it reflects back the difference in the time, I'm saying as delta t. Now suppose this vessel is moving here with some velocity v, and I call this as an S prime frame, then this man outside will measure this mirror mirror has to move from, say earlier it was here, it will move in the time, and he shines the light and it travels this extra distance. So say suppose this is c times delta t1. The time taken here is say delta t1 prime, and it gets reflected. Again, this end of this vessel will move in this time, say v delta t2 prime. So the time taken by the light is say delta t2 prime. This time taken by the light to come from here to here is same as the vessel moving from here to there, because this is the same time. So he measures the total time for the light to reflect back to this end is delta t1 prime plus delta t2 prime. So here I have written here that in a forward direction this is nothing but L, this is N, plus this much the vessel has moved, so this time also I have added. And for returning back, this is the distance L, say, and but this has moved, so you have to subtract this. So I have written here V, this is delta t2 prime taken for the light to come to this end, and in the meantime the vessel also has moved from here to there. So these are the two equations. So I bring this to the left hand side and take delta t prime common. So this will be c minus v, so L by c minus v, and during the way back this delta t2 prime is similarly, it is you bring this minus will become plus, so take the common factor. So this is the delta t2 prime is L by c plus v. So as I said earlier that I now add these two delta t1 prime and delta t2 prime. So from here when I add it, I get, this, you do the cross multiplication. So you get this. So you get this delta t prime as this quantity. Now I know this delta t prime, this is moving frame, and we derived earlier, that is a time dilation. This is your delta gamma times delta t, which we proved earlier. So I use it here, this one, and I know this delta t from here, that is nothing but 2 L naught by c. So I substitute it here, and this quantity delta t prime, this one is equal to 2cl divided by c square minus b square. I write it here. So now if I equate these two, I will get here, this is c square, I take common. So if I take common, this will be 1 minus v square by c square. So c square is common, this 1c with this common c square will get cancelled, remain 1c, and this c will get cancelled with this c. So if you do this algebra, you will get this is L naught by square root of 1 minus v square by c square. So this is your gamma, and this is 1 minus v square by c square. So now if I take this numerator to here, so this is square root. So what I will get is L is equal to this L naught times this, when I bring it to the numerator, this denominator, this is square root, so it will get cancelled. So I will have length L is equal to square root of 1 minus v square by c square L naught. L naught is the length at the stationary, and this L is in the moving. So I will get L naught by gamma. And since gamma is greater than 1, so I can say that where gamma is greater than 1, so I can say that L naught by L, okay, L naught by L is equal to gamma, and since gamma is greater than 1, I can say that L naught is greater than L. So here one can say the length of the moving rod appears to be contracted. So this is your length contraction in special theory relativity. So what is length contraction? Length contraction is observed by an observer in the stationary frame when they measure the length of an object moving with the moving inertial frame of the reference. So when it is measuring the length in the moving inertial frame and standing in a stationary frame, so it will appear to be shorter. So if it goes at very high speed, it will, as the speed increases, the length will become shorter and shorter, and if it goes almost to the speed of light, the length will diminish. So time dilation is observed by an observer in the stationary frame when they measure the time interval between events occurring in the moving inertial frame of reference. So in the moving inertial frame, when he measures the time there, he finds that the time has dilated. That is delta t prime is equal to gamma delta t, where gamma is greater than 1. Okay, now let us talk about Lorentz transformation equation. What does it say? Suppose you have two frame of reference, S which is stationary and S prime which is moving, and suppose this moving frame takes the particles, this point P with it. So how does he measures this position in this moving frame? So let us see how to find it. And here I have taken y prime is equal to y and z prime is z, because it is, this frame is moving only in the x direction. So now we know from here that this distance for an, this point is moving in this frame, this is x. So what is the measure of this x prime in this moving frame? And this frame is moving with velocity v, and the distance it has traveled is v times t, because you know that velocity is distance per unit time, so velocity in time will give you distance. So here, according to A in frame S, x is equal to, I write vt, and this and knows that this distance will be contracted contracted by this factor, square root of 1 minus v square by c square. So this is what this plus this is equal to x. So what is x prime for an? X prime will be your, this vt, you take it to the left hand side. So x prime will be x minus vt divided by this square root, and 1 by this square root is gamma. So x prime is, so one can know x prime in terms of x and t. Similarly, suppose this point P is in the x frame and this x frame is moving in the negative direction now. So Bob will see this frame is moving with negative velocity, this s, and this is the time for the Bob frame of reference t prime, and it will see that from this coordinate to this point the length has contracted, and this is your x prime, this is the point for the s prime frame. So according to B in s prime frame, I can write this x prime is equal to nothing but this minus vt plus this. So here I have written minus vt prime, this is the one, vt prime plus this. So I can write this vt prime, x prime I can substitute because I have got it here. So vt prime I take it, this negative will become positive, and this x prime I bring it here, which is gamma times x minus vt. In this term I divide and multiply by square root of 1 minus v square by c square. So I get rid of the square root, and 1 by square root of 1 minus v square by c square is gamma, which we know. So this is this term, and now I can expand this. So if I expand this, I will get this term, and this is gamma is constant, this is minus x is here, this x is here, so this x will get cancelled, and here this v will get cancelled, this is v, so I have vx by c square, and this v get cancelled. So this is plus and minus, so I have just written this plus here and minus here. So t prime is, so this is the second Lorentz transformation for t prime in terms of the stationary frame t and x. So similarly, one can get the reverse transformation. That means you change the sign of the velocity here. Okay, here also. So we know that gamma x plus vt, if you do this, you will get x here. And similarly, here I have changed the sign minus v to plus v. If I write this, and if I just simplify it, I will get this as t. So I can write this x prime, this forward Lorentz transformation. This x prime is this gamma times x minus vt, and t prime I write it here. Similarly, x is your this term and t is your this quantity. So this is your forward Lorentz transform, and this is your backward Lorentz transform. Now we'll talk about world line of the speed of light. What it means, suppose this is your y-axis, I now take it as time t, and this is your distance position, and we know that light speed is so if I plot in this coordinate system, this is your 1 second, this ray of light is almost falling on this x-axis, the position axis. So to make it better, I can scale this by 1 light second. So 1 light second is 300 million meters. So I have just squeezed this. So this is 1 light second. So if I squeeze this in 1 second, it will go 300 million meters. And now you have, this is in 2 seconds, it will go twice 2 light second distance. So now I have this light ray, okay, which is also called the world line of the light. This is 45 degree now. This is, you can see here, this goes diagonally. This is 1 and 1. So this has to be 45, this is 90. Okay, sum of all the internal angle of a triangle is 180. So 45, 45, 90 is 180. Here you can see, since v equal to c, that means your x by t, I can write is x by t is equal to c. So x is equal to ct, I can write. And your dt by dx, that is, this is y, dy by dx, that is the slope, dt by dx will be your 1 by c. So it implies that 1 by v equal to 1 by c. So this implies v equal to c. So for any line in this colored region, this will be greater than 1 by c, greater than this slope. And since this is greater than this slope, so I can write this is your 1 by v, because dx by dt is velocity is greater. So if 1 by v is greater than this, so that means c is greater than v, or v is less than c. So in this region, your velocity will be less than c. And in this region, this white region here, velocity will be greater than c, where I have shown here dt by dx is less than 1 by c. So your dx by dt is v, so 1 by v is less than 1 by c. So I can write that v is greater than C. Okay, I get C here and get the V in the right hand side. So C is less than V or V is greater than C. So this region is inaccessible. There is no particle which can, this we will see in our next few slides. Now we will discuss relativity of simultaneity. So here I have shown a figure here. Train stationary with respect to position, is not moving, it is stationary, and shines a light and gets this is the time axis. So the halfway and this reflection time, this is d by c, and similarly t2 is also d by c, where this d is the length of the train. So this halfway time which is here and this reflection, they are simultaneously for both this observer, and since the time is moving in this direction, so this at same time this reflection and halfway time is same. So one can say that for stationary train but moving in time, the halfway time and reflection are simultaneous. For Anne and Bob, lines of simultaneity are horizontal. So the simultaneous line of simultaneity means any event which are happening, they are horizontal to the x-axis because time is in this direction. So all positions are at the same time. So all position in this horizontal direction, they are having the same time because time is in this direction. So any event happening here will be simultaneous. So now we discuss what happens in motion. That is, we know that in motion the time axis get tilted, and to maintain the simultaneity we will see that the position axis also has to be tilted. Why? Because this is your time axis which is tilted. This train is moving here, so this is the time axis. This is for the stationary frame, and say this is the halfway time for the light to go from here, from this point A to point B, and then again returning to N from B to A. And here you see the time taken stationary frame, the halfway time is t1, and the time taken from this point to this point is time t2. These are not equal, and since we know that this event, this halfway time and this reflection in a moving frame will be simultaneously, so this your horizontal x-axis will be tilted to x prime, because in a moving frame these two events will be crossing the t in the same point, and if it is not tilted, then this half time here, and then when it moves, so in a moving frame, so you will not see this event simultaneously. And that is what one observes by the stationary frame, when two simultaneous events occurring in a moving frame will not be simultaneous. We will see this in our future slides. So from the frame of Einstein, T1 is not equal to T2. Of course, we saw it. The line of simultaneity from Einstein's point of view for A and B are diagonal. So if they claim that this is simultaneously, so Einstein will say, okay, then your x-axis, the horizontal axis, are tilted. They are diagonal. So here I show an animation where this horizontal axis, x-axis, it goes, all the point in the x-axis crosses time simultaneously, and when it is tilted, so you have to tilt the x-axis also, and you have to move the x-axis in that tilted fashion, so that all the events occurring at x at the same time will cross the time axis at one point. Okay, now we will see that velocity of light is constant in all inertial frame. So here I show a figure, so please try to understand this figure. This will clear any doubt which you had in my past slide. So Anne is moving, so it's changing the position with respect to time, and this axis I take as the moving frame time t prime, and this is your stationary frame, this is t. And to maintain the simultaneity, that is, since this time is tilted, so your position axis will also get tilted so that the simultaneity is maintained. So these are all, this line, this is your position axis, this all the horizontal to this position, this is your moving frame x prime. So these horizontal lines will be all of same time, because they all this position is crossing at a constant this time t. So these lines are called constant time, and the line which are cutting in same position, these are called the constant position lines. And here I have shown this is cutting at 1 light year, this is the distance, and these horizontal lines are crossing this time axis. This is 1 second, 2 second, 3 second, and so on. This ray is a light's world line. So these are called constant time in S prime frame. These are all these all are 2 second, because it's cutting at 2 second here. This is 1 second, this is 2 second. These thin black lines are the constant time in S frame. This is the stationary frame, and constant positions are these blue lines, light blue lines are are the constant position in S prime frame. Okay, see, all their times are different here, but position is same. And these vertical thin black lines are the constant position in S frame. So with this understanding, I can say that the time axis and the position axis tilts forming a parallelogram. So they tilt and they form a parallelogram. Rhombus sides with equal length and equal angle with respect to light beam, 45 degree. Light beam is at 45 degree. Okay, so this angle and this angle will be same with respect to the light beam. So it is like a scissor. So as the speed increases, this will come closer to the light world line. Similarly, position axis will also come closer. So this will squeeze in this direction towards the light world line. Thus, light travels 1 unit of distance in 1 unit of. So here this is a unit of distance and these are the unit of time. So the light will travel 1 unit of distance in 1 unit. Thus, the velocity of light is constant in all inertial frames. So velocity of light will be constant because the slope remains same. This is your light world line. But with speed, this slope will change. So as the speed increase, this slope will tilt towards the world line of the light. So similarly, this angle has to be always same. Time axis have constant positions. So time axis will have constant position. So this is a constant position here. Okay, all these positions are same. And similarly, position axis have constant time. The position axis will have constant time. That is, all this value of positions will have same time. Now we will convert time axis t to a unit of distance. That is, t is equal to c into. I will just multiply by velocity the time axis to get distance. C is what, x by t. T get cancelled. So this is a dimension of position. So here I have done this. Okay, ct, use ct as a single variable having unit of distance. So here I have written this 1 meter the light will cover in time 3.33 nanoseconds. So now I have, earlier we saw that your slope was t by x, that is 1 by c. So this is not equal to 1. So if I multiply by c, so I will get the slope 1. That is, if I multiply time with ct, now this t by x is 1 by c. So this slope is 1. Now here I have shown here the slope is 1. So x is equal to ct. So this is the world line having slope equal to 1 and is 45 degree from the x-axis and y. And here y-axis is nothing but c times t. So here I show the similar thing. This is the particle moving with some velocity. Distance travel is x is vt. So this x is equal to vt I can write as x equal to v by c times c. So that is x is equal to beta times ct. And similarly, this slope here which I have put here, this will be inverse of it. You can see from this figure also. So this is 1 unit 1. So slope is 1. But here you see this travels a distance 1, but in time it is 2. So 2 by 1, beta is 2 here. And similarly here it travels distance 2 and time taken is 1. So this is 1 by 2, that is half. So beta, as I said, was 2. So this is half. So here your slope is 1 by beta. Here slope is beta. And here we have shown that this x is your, this v by c is 0.5 of the speed of light. The velocity is 0.5 the velocity of light. This is 0.5. And if suppose velocity increases, this axis will get tilted. And as velocity moves towards c, it will collapse to the world line of the light. And here beta is a, as I mentioned, is a fraction of the speed of light. That is, b is v by c. Now we will discuss scaling by one single linear factor gamma to both the axes. So when you tilt it, you have to scale by same single linear factor the time axis and the position axis. So let us see what I mean here. So this diagram looks a bit complicated, but it's not so. So here I have plotted the time axis, that is ct, and this is the position axis, and this is your world line of the light, and this is the prime axis, time ct prime. This depend on the velocity of the particles, that is v by c. So if the v by c ratio increases, this will collapse, this will move towards the world line of the light, and similarly this angle should be same, so position axis also will move. So here I have plotted, this is your x is equal to vt. This is the thing, because beta is your v by c, so this is x is equal to beta. And as mentioned earlier, this slope will be, your x will be 1 by beta of ct. So this is ct is beta x. So this is the equation line of this axis, and we see that this separation here, this beta ct, as time increases, this separation will increase. So this position here, this is a vt, that is beta times ct, and similarly here it will be this ct I have written as beta x. So as position increases, this separation will increase, and the slope of this is your 1 by beta, and this slope is beta, which we have discussed earlier. Now you see here here, suppose if I have this distance here is x prime in the prime frame. So this x prime is nothing but this distance from here to here is x minus beta ct. This is your x prime. So this line will be x prime is x minus beta ct. And similarly here, this distance from here to here, this distance is say ct. So ct minus this beta x is ct prime. So now I write these two equation here, and you see very interesting. Suppose when this is a stationary, is this s prime is moving and s double prime is also moving with twice the velocity, and if the thing scales as x, so your s prime by s is say x, and then again it scales by x, that is s double prime by s prime is again say x, some linear, some x. So your x prime by x is your x, and here x double prime is your x square by x. X prime I said is x, is again x. This obeys. But suppose this transform not linearly, say some power I have taken for simplicity, say square, then your x double prime will be, when again it is x prime square, is x to the power 4. So now if I take this x prime by x as x here, and this x double prime, that is x to the power 4 and x prime, so this is x is not equal to x square. So if you do the transformation with any other power, you will not get, you will get some non-linearity. So to maintain this, the proportionality constant here gamma, which I will say here, has to be linear. So here I will say that since all the sides of the square are equal, this square are equal, and similarly for rhombus, to make both the areas equal, we need to scale by only one single factor to both the axes. Also to maintain this area also has to be same. So single factor to both the axes by single linear factor, say gamma. So here I have written that this is the scaling factor gamma, and we have really seen what the value of gamma is. So now let us find what is the value of this gamma for this Lorentz transformation. In a linear transformation, scalar multiplication and additions are preserved. So as I mentioned, what is the area before and after Lorentz transformation? The area remains same. So this area remains same of the square and the rhombus. So this is the forward transformation, and I change this velocity v to minus v, as we mentioned, discussed earlier. So this sign changes plus. So now since the velocity of light is constant in all inertial frame, I can write x is equal to ct or x prime is equal to ct, because 45 degree to these two axes as well as, so when it is 45 they are equal, x is equal to y, or that is y is ct here, y is ct prime. So I multiply this x into x prime, I get here x prime, x is I am taking from here, and x prime I am multiplying it here. These are trivial algebra, please kindly go through this step, it is not very difficult. So here x is equal to ct prime, I am writing the same thing here, and then I am just expanding this, and this two term will get cancelled. This is ct prime into ct and beta square ct into ct. So this is what I have written here. Plus into minus is minus, and this minus plus will get cancelled. So now I take this ct prime ct common here, so this will get cancelled. 1 minus, this is 1 minus beta square. So gamma is equal to, this is gamma square. So this numerator will go to denominator, and when I take a square root, so gamma is equal to 1. So this is the Lorentz factor gamma, and since beta is v by c, it becomes 1 minus v square by c square. So here I have described that how this is a stationary frame and this is your moving frame. This is tilted, the time axis and the x axis, and we will show here that the area, this green area and this rhombus area or this orange area here, they are same. So it is very easy to show. So I can write this in form of a matrix. So I am just introducing matrix because in my next lecture when I discuss general theory of relativity, all this will be required. So let us slowly introduce bit by bit what is matrix, what is vector. We will discuss more in detail when we discuss general theory of relativity. So here I have written this here, ct prime and x, that is nothing when gamma is common. That is your in a matrix form, you write ct row and column, first element, then second element. So this is ct minus beta x, you get this, and similarly for x prime is into 1 minus beta ct is here and plus x. We also know that the determinant of this matrix will give you the area. So this is your gamma I have taken inside. So gamma square minus of gamma square into beta square. So the common gamma square I take it outside. So this is gamma square 1. And since gamma is 1 over square root of 1 minus beta square, so gamma square will be 1 over 1 minus beta square. So this will get cancelled, equal to 1. Now for this square, this grid, it, I can put this velocity is 0, so gamma is 1, and here velocity is 0, so this quantity is 0. So this also, the area, this is 1 square minus 0 is 1. So this, both the area are same. So the area before and after Lorentz transformation, the area remains same. Okay, now we will see time dilation using Lorentz transformation, that is moving clock runs slow, which we have seen earlier. Now we are going to see that's Lorentz transformation also gives the same information. So here this is your forward transformation. This minus beta become plus beta in the reverse transformation. That is when you are changing the coordinate from stationary to your moving frame or vice versa. Now let us concentrate on this. So here again I have drawn CT in this time axis, and this is the position axis, and in the same position in the stationary frame A and B, this is in the same position. You have two different times, CTA and CTB. These are the two events, and in a moving frame your CTA prime and CTB prime will be here. So here I have shown two events. This is your shining the light here and bouncing back and coming back here. This is event A, this reflection, and coming back is event B. So if delta t is measured in a rest frame, so delta t is the proper time. So in any rest frame you measure time, that is the proper time. So now I write from this equation, this I have written delta t prime because I can take two differences of this. This is a difference in time. This is your again difference in time in the stationary frame, and this is the difference in position in the S frame, stationary frame. But in the stationary frame we saw that XA and XB are same, so delta x is 0. So delta t prime is gamma times delta t. Okay, since this is a stationary delta t, this I can call it as delta tau. This is a proper time. So this is what I have substituted here. So I call this as a proper time, delta t is equal to delta tau. Now again, if I take this event A and B along this axis where XA prime and XB prime are in the same position, so the time taken in the same position will be your proper time, delta tau. So here what I have written here is C delta t, from here I have written here, and since delta x prime is 0, so this delta t prime is your proper time. So this is what I have written. So here also I have written that delta t prime is measured in the rest frame, so delta t prime is delta tau is the proper time. So what I mean is this is two position time, and this gamma and time taken at one position. So this is taken at one position, so this will give me a proper time. These are also taken at the same position, so this also will give me a proper time. So I can write that two position time, this is delta t, is equal to gamma times delta tau. So in whichever frame you measure time at one position, it is called delta tau, and at two different positions is called delta t. So I can write delta t is gamma times delta tau. So I can write this in a differential form, that is dt by d tau is equal to gamma. So proper time delta tau is the time measured by a clock that is in a rest frame. As I have shown here, these are the rest frame, means positions are not changing. Here also this position is not changing, so this is delta tau, this is delta tau. And so in the observer's reference frame, the observer time or two position time is always greater than this two position time. This gamma is greater than 1. So this is the two position time will be always greater than delta tau. So in an observer reference frame, the observer time or two position time is always greater than the proper time. So proper time is in the rest frame where the clock is moving with that frame. If you are stationary and measuring it, you will always have time dilation. So this proper time, which is a one position time, so this effect is called the time dilation. Now similarly, let us discuss length contraction using Lorentz transformation, which we called earlier that moving length contract. So here again I have written this position transformation. This is x prime and this is x. So let us concentrate here on this figure. This is your, as usual, the time axis, and this is your position axis. Here we have taken rod moving with s prime frame and measured from s. So if I see here, delta x prime is, I am using same thing, difference of these two, take at two different position, and since here delta t, this is 0, I get delta x prime is gamma delta x, and delta x prime is stationary, I call it L naught, and this is gamma times L. Delta x is this one. So here gamma is greater than 1, so L naught will be greater than L. Similarly, we can see that you have same time axis and the position axis, and now you take here this length, this object A, and this is B. This is the distance delta x prime, and this is your distance in the stationary frame delta x. So this distance I call it L naught. So this is not dependent on the time, because you measure at some time and then go somewhere, then again come and measure the end of this, the distance will remain same, okay, because this is stationary. So this is your L naught, and now this is in moving frame, this is your delta x prime. So here I have said that rod measured from s prime frame rod kept at S. So the rod is kept in the stationary frame. Here this time, this C T prime A and T prime, this is the same time. It crosses the time axis same. So here I have written measured at same time T prime. So if I again write from here, delta x is delta x prime plus beta times C delta T prime. Now delta T prime, since it is measured at the same time, is 0. So delta x is gamma times delta x prime. So your this delta x is your L naught is gamma times L. Delta x prime is your L. This is the length. So here since gamma is greater than 1, so L naught by L will be greater than 1. So L naught will be greater than L. But here you observe one thing. Note that delta x prime, this delta x prime appears longer than delta x. But here you are saying that this is greater than L. So in this type of coordinate system, which we will discuss in detail in further slides, here you take this space-time interval as this delta x square minus c delta t square. This is a space-time interval. This is always, as we saw earlier, that they are same whether in stationary frame or in reference frame, this quantity. So if I substitute this delta t prime is 0, so I get this equal to delta square, and this c delta t I can substitute as the c delta t as beta delta x. So if I write it here, I will get delta x square, you can take common, so 1 minus beta square. So 1 minus beta square is 1 by gamma square. So taking the square root of this quantity, I get delta x by delta x prime is gamma. So always this delta x is greater than delta x prime for this. So it looks larger here. So this happens because now you are mixing space and time. So not like in a Pythagoras or in an Euclidean geometry where you only deal with space but not in time. So these are some of the things which appears or pops up when you mix up space and time to make a single coordinate system. So proper length is the length of an object measured in an inertial frame where the object is at rest. This is the definition of a proper length. Now velocity addition using Lorentz transformation. So it is interesting to see that if suppose you have this S prime is moving with some velocity v and S double prime is moving with respect to S prime with u, so it is not simply getting added up v plus u. That happens in the earlier Galilean transform, but here it is not so. So in relativity, we'll see how does it look like. So these are your Lorentz forward transformation I have written in matrix form, which I had introduced earlier. And this is your transformation from this to this here. And then from S double prime to S prime, you write like this. So these green betas are for this. These red betas are for this one. So you can write this as this C T double prime. I can write as this is your transformation, which I have written here. Then you have this C T prime X prime. I substitute this here. So I get this. So I get this coordinate with respect to this CT. This is a stationary. So if I do this, I bring this gamma u gamma v here and I do the matrix multiplication, that is 1 into 1 minus beta u times beta v, then 1 minus beta v, that is beta minus beta v, and here into this, okay, row and column. You have to multiply row and column. This is first row first column, then first row second column, then second row first column, second row second column. Okay, so if you do this, here it is your minus beta u beta v, so minus minus plus beta u beta v times 1 into 1 is 1 plus. Now here I make this entity as 1 as I had done it here, 1 1. So for this I take this 1 plus beta u beta v outside, okay, this 2, and divide this by 1 plus beta nu beta v. So here what I have done it, I have taken this common factor out, and here since I am multiplying this by this term, so I divide by these terms. And now I simplify this one, this gamma v gamma u times 1 plus beta u beta v. So gamma v I have written as 1 minus beta v the whole square, okay, v square by c square, and this gamma u gamma v gamma u gamma v, this same thing I am writing as square root and then squaring it. So this is same, and now I take all of them under the square root, okay, just expand this and there will be some term which will get cancelled, this 2 term will get cancelled, and you can simplify to, this is same thing I have written here, and you can simplify to this 1 plus beta u beta v square. So now I can write this c t double prime x prime as this as, and this I am writing it here, that is square root of, this is I am dividing it by 1 plus beta u beta v square. So here I will get this, so 1 divided by 1 minus this thing, and same thing this one I have written it here, this and this. So now this quantity I can write this in green and red, this beta, the whole thing I can write as some other beta and representing as blue, okay, this is this beta. So I write where beta is bu plus bv. So now bu and bv I know is u by c and v by c velocities. So this is your velocity addition. addition. This is v by c. Okay, the c's will get cancelled, and so now you will get velocity. The sum of the velocity is not u plus v. Okay, which it will be u plus v divided by 1 plus uv by c. So here you can see that if the velocity increases to c, that is c plus c. Okay, it's twice c, and this is your c square. So twice c divided by 2 will be c. So you cannot exceed more than the velocity of light. So anyway, we will discuss this as we go along. Now we will discuss speed of the light is a limit, as we discussed earlier, that you cannot keep on adding the velocity by increasing the velocity of the reference frame. So here's what I have shown here. So this is stationary, and this s prime is moving with some velocity with respect to s, and this s double prime is moving with some velocity u with respect to s prime. So you cannot keep on increasing the speed by increasing the velocity of the inertial frames. So here this is what we have seen in our last slide, and this is your standard form from the matrix to standard form. This is ct prime. This can be written in a matrix form, and this beta, this velocity addition which we have seen in our last slide, where beta v is v by c and beta u is u by c. So now here this is a condition, that is velocity if is 0, it is 0 definitely, but if you increase the velocity, say bu and bb, and since v is always less than c, this will be always less than 1. This will also be always less than 1, so it will be always less than 2. And similarly, you have this quantity 1 plus, this also will be, since this is less than 1, this is less than 1, so when you multiply it will be less than 1. So this 1 plus some less is always be less than 2. So beta is always less than 1, this quantity. So suppose if beta v is 0.9 and beta is 0.9, that is v by c is 0.9, that is velocity is moving at the 90% the speed of light. If you add it, this 0.9 and so you get 0.9945. So in this frame you will only see it will approaching to velocity of light, but with increasing further and further the reference frame, it will never increase the velocity of. So here I said note, even after applying Lorentz transformation many times, you will never find any reference frame moving faster than light. Okay, now we will discuss simultaneity in special theory relativity. So if suppose a flash is made here simultaneously, Einstein will see it appearing simultaneously, but it is something like that. Suppose two flash occurs at the same time, and Einstein is moving in this time axis only, not in the position. So it will see the flashes occurring at the same time. And now suppose this A and B are moving with some speed, and maybe in this moving frame they are happening simultaneously, but in Einstein frame of reference, when Einstein is moving, this is your time, so it will see this flash first, and then after some time it will see this flash. So it is not simultaneous for the Einstein, because this simultaneous flash is occurring in the moving frame. So similarly, if it is in the other direction, the order will reverse. This Einstein is stationary here, and this flash occurs, it will see first this flash A, and then it will see this flash after some time. And thus in special relativity, simultaneity is related. And here I have just shown this coordinate system which I have explained more or less. So here I am introducing this tan alpha, that is your opposite side is your beta x by this distance x. So tan alpha is beta. Similarly for here also tan alpha is bct by this is the time ct here. So beta ct divided by ct. This is your tan alpha is again beta. So this is again how to represent this A and B in x and y axis. Your xa, this is your xb, and similarly since this is tilted, your all this space thing, this constant x will be along this parallel to this ct prime, and your time, constant time will be parallel to your this x prime axis. So this is all constant time. So this is constant time, and this is your constant in x prime in s prime prime, and this is also your constant. This all positions are constant, but time is changing in ct prime. So just have a look. It is simple to understand. Okay, now we will discuss effect always follow the cause. Now suppose this event occur because of this blue event occurring. So if I move along this, so here I see, okay, this event has occurred, and then this event has occurred, and this event has occurred because of this event had occurred. So similarly, if you are in a moving frame, suppose this is your event, okay, because of this event, because of this cause, this is the effect. So here also you see the cause. Even if you see in this first you will see this is your cause, this is the first, and then in a later time CT prime. And similarly, if this is your for stationary, if this line moves in this, first it will see this one happening, okay, the cos, and then at some later time it will see the and then at some later time it will see its effect here. Okay, this is time. So similarly here you see that now it is tilted in the opposite direction, it is going with the opposite. So here also this is the cause and this is the effect. So if I move here, this happened first in the time axis and then it happens later in this CT prime. And here also when I move in the stationary frame, I will see this first and then I will see this. And but if suppose you are going at such a high speed that you are gone outside the cone, so this is your CT tilde is not in this yellow region but it has gone in this not allowed region, then things will be different. So here you see this is the cause, this is the effect. So here what you see is that now this is the time axis and this is the position axis. So parallel to this position axis will be cutting the time axis. So here you see if I am moving from here, I will see this effect happening first and then as I move I will see then the cause. So let me show it more better in a pictorially what I mean by this. That is, if this is velocity of this particle, or if this is a gun, this bullet is going at faster than light, and this is your light cone and this is your position, this angle has to be same. Now if this is so, if this time axis is in this non-accessible region here, then what you will see, suppose you draw, this is your time, you draw this is the position, so you have to draw parallel line across this, so this is your time. So what, as I move here, first I will see here this light ray will come here, you will see the bottle breaking, then I will see the bullet is flying, and then when I move I will see it is firing. So it violates the causality. So bottle breaks before the gun is fired. So you cannot have this time axis, this is not allowed region. So you cannot have velocity faster than the velocity of light. So moving faster than light violates causality, that is one see the effect before the cause. Time runs backward. Okay, so there are many papers on it. So there are many papers and even movies about these things. So now it is up to you to ponder about. Now we will use Lorentz transform to show that the space-time interval between any two events is an invariant. So here I have shown this graph. This is your say point A and point B, and it can be represented in both the coordinate. This is your XA, this is your XB, this is your XA prime. So this will be parallel to this. This is the position and these are the timeline. These are the position lines in the moving frame. Similarly, like what you have in the stationary frame, parallel lines, these are the timeline and these are the position lines. This black in the stationary frame and this red dash lines are in the moving frame. So I use this Lorentz transformation here where C delta TAB is this distance, that is CTB minus CTA, and delta XAB is your XB minus XA, and I can write this the space-time interval. This is C delta T prime square minus delta X prime square. I just substitute this here. So if you substitute this here and then square it, so you can take this C delta T the whole square term common. So this will be 1 minus, here this beta is there, C delta T square. So this beta square will come because there is a minus sign here. So similarly for delta X square you can do, and other cross term will get cancelled. Now you take 1 minus beta square common, and this is C delta T square is here, delta X square is here, and this gamma square and 1 minus beta square will cancel because gamma square is 1 over 1 minus beta square. So this will get cancelled. So you have the space-time interval in the moving frame is equal to space-time interval in the stationary frame. So using Lorentz transform you can show this. So here are some examples. This is a point A and this is your 1, 2, 3, 4, X is 4 and T is your 5. Similarly, by substituting here you can get X prime and T prime by substituting X, this 4 and 5 here. So here I have taken V is 0.5. So T square minus X square is this 5 square minus 4 square is nothing but your 3.5. I have written here prime so that is 3.5 to the square. So is approximately 9. Similarly for point B, the distance from origin to this is your 2.9 here and this is minus in the T direction. So minus 1.15 square minus 2 point. So this one is equal to, in this prime axis if I substitute this X and T, I get here minus 3 square minus 4, this is equal to minus 7. And similarly you can also show that this distance A and B is equal to 36.6 whether you do it in prime frame or you do it in stationary frame. You just do this 5 minus of minus 1.5, you substitute all this and you will see that this comes to be 36 whether you do with respect to to unprimed frame or with prime frame. So note S square can also be written as, instead of delta CT square minus delta X square, you can write also, instead of here with what I have written, you can also write like this. So the magnitude doesn't change. Maybe the sign may change sometime, but stick to it for some calculation. Now this is the famous paper by Einstein, which was published in 1905. Does the inertia of a body depends upon its energy content? This was the title of the paper. So here the main idea is that you have a particle here, and this particle can emit 2 photons. So this is the initial energy before emission. This is E0 is the energy before emission of the, after emission of the energy is, say, E gamma plus in the, and this is E gamma minus. So here I have written Einstein notation, E gamma plus. This is a half of L. This is the light energy L. So half light energy goes this side, half light energy. So total light energy is E gamma plus E gamma minus. And if the particle is moving, so this is the energy of the particle when it is moving, and after emitting, this is H1. So moving particle is been denoted by H here, and this is after emission. This is in the moving, and this is stationary. And total radiation is E prime gamma plus E prime gamma minus. This is not in the paper, but this is shown for understanding it better. So here, these are the things which I have taken from his. So E0 is your E1. This energy has to be conserved. So E0 is the initial energy, and the final energy is this E1 plus this 2 energy, okay? Half L plus half L, where L is a light energy. And for moving frame also, this is your H0, this is the initial, and then when it emits, this is H1 plus. Since it is moving, I will derive it here. This is your Doppler's shift equation. This is 1 minus V by C cos phi, and this is your energy will also change for this moving, one in negative V direction, one in positive V direction. So your H, this energy H0 is H1 plus. If you add them, this will get cancelled, and you will get half L plus half L, L plus 1 L, and square root of this is a common 1 minus. Now if you subtract this energy from this energy H0, so I can get this, I can get it in the H1 minus E1, I can get it in the left hand side. So H0 minus E0 minus H, so that is equal to this L square root of 1 minus this is L, so minus 1 here. So now here I can write this H0 minus E0 is nothing but the difference energy is nothing but this kinetic energy before emission, and this is the kinetic energy difference after emission, is K1. So I can write that K0 minus K1 is equal to, this is your K0 minus K1 is equal to this. Now I can expand this in the Taylor's expansion, square root of 1 minus V square by C square. The Taylor expansion will be 1 plus half of V square by C square. So 1 and 1 will get cancelled. So you will have only half left here, half. So L V square by C square. Just check Wikipedia for Taylor's expansion. And this difference before and after in the kinetic energy is due to the energy given out in the radiation. So one can write that if a body gives off energy L in the form of radiation, okay, this is the energy, its mass diminishes by L by C square. So the mass has been this kinetic energy like 1 by mv square this. So one can write this m is equal to L by C square, that is E is equal to mc square. So this is the famous Einstein's E is equal to mc square equation, and I have done it very shortly. Plus, so please go through this paper to understand the philosophical part of. Now we will discuss this Doppler shift which has been introduced here. So if you know that when this sound wave, when this is a police, this siren, so this sound waves, the equal number of this side and that side, so this get compressed here. So this wave will come quicker and quicker, whereas this and this direction it will be at a longer separation in time, and here it will be coming in quicker successions. So this will be having higher frequency than this one. So this is the angle theta. So this frequency, this beats coming or pulses coming per unit time will decrease, and here it will be the least. So this is what is Doppler's effect, and it is easy to see Doppler effect formula for the frequency. This is a very short quick calculation. More elaborate and extensive calculations are given elsewhere, but maybe for understanding it is not required now. So again I take this Lorentz transformation and I can write this delta t, I divide by c here, delta t prime I keep it here, and this v by c square delta x I am writing is as c delta t. So one c will get cancelled with this c delta t prime, and so I have introduced angular dependence on this in this term. So if I use this, I will delta t prime, I take it out, this is common. So this is 1 plus v cos theta by c. So delta t is gamma times delta t prime 1 plus v cos theta by c. But we we know that delta t is related to energy. Energy is nothing but h times frequency. Frequency is 1 by delta t. So I substitute this delta t here, this term, and then I will get this is your E is equal to your h by delta t prime, and gamma will come to the numerator here, 1 plus v cos theta by c. And then h by theta prime is nothing but h times v prime, okay, in the moving frame, and that is the energy in the moving frame, E prime. So here, that's why in the moving frame it is either 1 plus v cos phi c, and if suppose cos theta is 180, it becomes minus. So this is how one can understand the Doppler effect formula for frequency. Okay, now we will discuss velocity dependent event traces hyperbola in a spacetime. So what do I mean? Suppose Einstein has a firecracker and it all burst in 10 seconds, but if he has firecracker having different speed, then he will observe that the one which is lower speed is here, this is your higher speed, this is still higher, here I have written, and the one with the higher speed, the time taken because of time dilation, the moving clock runs slow, so Einstein will see at a longer time. So, and if these events are plotted in a graph, you will see it obeys a hyperbola. So we will discuss what hyperbola curve looks like and how you get it. And here I say the equation of hyperbola is y square minus a square minus x square by b square equal to 1. So this is the equation of hyperbola. If a and b is 10 seconds, I've taken as 10 seconds, and y is t. So this will be the time taken for the firecracker with respect to Einstein. As this x square increases, the time will increase. So to continue, this single coordinate traces hyperbola upon increasing velocity. That's what we saw earlier. So let us do some example and see. So here you see this is a coordinate, and this is your point P here. This is a moving frame, and this point P has a value of x as 0.75 and 1.25 in the CT axis in the stationary frame. So we plot here a single coordinate point 0, 1. So this is, I have written prime here because it is in prime frame. So this is your x-axis is 0 here, and time is 1 because x-axis is 0, then 1. So this is at 0, and time axis is 0, 1. So this is at 1. So I have written 0, 1 for many different velocities beta using the Lorentz transformation equation for x. That is, I have plotted here for different values of beta. So let us see whether how you get this. So as I said here, for p, x prime is 0 and ct prime 1 on a hyperbola is labeled as point p for a velocity of 60% the speed of light. So using this Lorentz transformation equation and using velocity is 60% 0.6, I get gamma is equal to 1.25. So substituting from this equation, this gamma and x prime, I get x and ct as 0.75 and 1.25, which I explained earlier here. This is a zoomed region of this one, 0.75 and 1.25. So here there is a table for different velocity, and the point P will trace this x and ct you will get. So this will trace this blue path. An interesting thing is that this s square, which of course you saw it is as 1 square minus 0 is 1, and similarly this ct minus x square, from here you take ct minus x square is again 1. So ct minus x square, you can see this is your ct minus x square. This is your ct square minus x square is plotted here, and all of them will give 1. So whatever the distance from here, these are all different velocities. So the distance from here to here is always 1. Now a bit of elementary school stuff. This is the equation of motion. Now how this hyperbola comes about, we will start from very elementary. This is a notion which you have to understand what is happening. This is equation of motion. So for a circle, this is the equation of motion. X square plus y square is r square. That is x square plus y square. You can use the Pythagoras theorem. This is your r. This is x square. This is x distance. This is y distance, r. Similarly for ellipse, you have two focal point, and this length is constant. You can see if you tie a rope here, same thing. And here it is in more clarity here. So these are the two focal point, f1 and f2. So here d1 plus d2 is constant. See, if this is the thing here, there you have extra. Suppose this point is here. So you have from here this red line here will go and then come back up to here. So here you have twice. So this is your 2a. Okay, this is your say minus a to plus a. So it will be twice a, this distance. The length of this thread by which you draw this ellipse, it will be 2 times this a distance. So here, as this r was constant, when you rotate it, it makes a circle, and here when you rotate this, with two focal point, you get an ellipse. So with this condition, d1 plus d2 is 2a, I can solve. Okay, what is d1? d1 is y2 minus y1 the whole square plus x2 minus x1 the whole square. That's what I have written here. Okay, this b square minus this c. These are very elementary stuff, but just for completeness sake, that what you really mean by this path. So there are certain constraints which determines the equation of motion. So there the constraint here was this radius of the thing. If the ball is attached here, this is the constraint. It can only go through this stick. This will obey the circular path. With this constraint, d1 plus d2 is twice a. You can only get an elliptical path. So I will go hurry this one because it is becoming too lengthy now. So this f1p plus f2p, again you do x minus of minus, this is plus x plus c the whole square plus y square, okay, y minus 0. So these are very elementary two-way. You get this one in the right hand side becomes minus, and then you square it, okay. So you square this is 4a square, twice of this one is your minus 4a this, and this square root will go off when you square it. Now you just rearrange it, this 4's will get cancelled, and you will have this cx minus a square is equal to this. Now square of this, the square root will go, and this will become a square. And similarly, you simplify it, you bring this all x square term in one side and y square term and this constant terms here. So you will get here something like this, okay, and you will get this, and divided by, you take this and divide by a square b square, you will get x square by a square. So this is the equation for the ellipse. So similarly for parabola also, this is your parabola, okay, in this, and here the condition is this distance eg and ef is constant. So for a parabola, I can, with this condition set ef is equal to eg, I can do similarly, okay. So this distance is x square, x minus 0 the whole square, y minus p the whole square, and square root you have to take. That is equal to your eg is x minus x is 0, then y plus p the whole square is. So just square it and rearrange it, you will get x square is equal. So this is the equation of motion of a parabola. So the path will go, this is your constant. Here you can see this is constant, this distance and this distance is same. Okay, now let us come to hyperbola, because this is very important to know what hyperbola means. If you do not know what circle and ellipse is, difficult to understand what hyperbola is. So in a hyperbola also there is a constraint. Hyperbola also you can construct, you have two focal point, and here you take this distance here d2 minus d1 should be constant, okay. So with this condition you can draw a hyperbola, you can trace a path of a hyperbola by keeping this constant. And these are the asymptotes, okay, it will slowly reach here, unlike in parabola. So you have an asymptote here, it will reach to this point as x tends to infinity, and here also this origin, and this is your say distance a, this is a diagonal c, okay. So from here when you cut it to the asymptote, this distance is called the b. So here a square plus b square is always c square, and but condition for making a hyperbola or getting a equation of motion, this is the condition d2 minus d1 is twice. So let us use this condition d2 minus d1. So this is also very similar to earlier one. So d2 minus d1 is, this is point x minus or minus x plus c the whole square plus y minus 0 is y square, square root of this. So this is the distance of d2. Similarly d1 also you can do x minus c the whole square y square equal to 2. You transfer this term to the right hand side and you square it again, what we did like last time. This 4 will get cancelled, and there are certain terms will get cancelled here. Just do it with pen and paper, and then you can rearrange it in this form. This is cx minus a square. Now you square it, so this a square and this square root will go off, and then you simplify this x square minus 2cx plus c square plus y square. So after simplification you will get this equation x b square minus is equal to a square b. Now you divide left hand side by a square into b square, you will get it. This is the equation of hyperbola. So if the asymptotes are at 45, then a equal to b, and for the hyperbola open at y axis, the equation, this is open at x axis, is open at x axis. For hyperbola which is open at y axis, that is hyperbola here, it is open at y axis. This is the formula, and this is for y square by a square, this is okay, and this is for the parabola. Now for completeness sake and also to understand an accelerated frame, this is very important to understand this accelerated frame of reference, so which we are going to do, because for circle we know that this is the area of the sector. So we know area of the sector is, this is your pi r square, and the fraction of that, fraction of 2 pi, that is theta by 2 pi, you take it. So pi get cancelled and r I am taking as 1. So theta is twice the area. This theta is proportional to twice the area, or you can say area is proportional to half the theta. Okay, area is proportional to half times the theta for r equal to 1. So similarly for hyperbola, this is a hyperbola here. This is your center, and interesting thing, what is the area under this? Area under this is also very similar to this. For circle, we saw that r is constant as you change the theta. Here we will see that this length a is constant as you change the phi. So it is like a circle only. This is a radius, it is called, and this radius of this, the distance between this and this in hyperbolic geometry will be same. We will see this, and as we go further, it will become clearer what I mean. And we know that for circular polar coordinate, this equation x square plus y square is equal to 1, and if I take x is equal to some r cos theta and y is equal to r sin theta, then I can always get sin square plus cos square theta equal to 1. So here we will take cos hyperbolic square phi minus sin hyperbolic square phi as 1. So instead of plus for the circular polar coordinate, we are going to take minus. So with this condition, we will always get this distance as constant. So this is like radius, but this is open in the x-axis. So this is like a perimeter of a circle which is open. So this is like the circumference of a circle. So this is, and center is here. Okay, because of this nature, we call it as a hyperbola. Okay, this is a hyperbolic condition. Anyway, as we go further, it will become more clearer. So this distance, I call it a cos phi or cos hyperbolic phi, and this is a sin hyperbolic phi. Okay, these opposites, and this point is your a cos hyperbolic phi and a sin hyperbolic phi. Okay, this point P. So the area of this a, I can say that area of this triangle, this is this base into height divided by 2. Okay, half base into height minus of, you take the integral from here, a cos hyperbolic 0, this phi is 0, to a cos hyperbolic phi, and this y is nothing but x square. As I said, in this case, x square minus y square is a square. So minus y square, I take it this side, and a square I bring it. So y becomes square root of x square minus a square. So now I substitute x is equal to a cos hyperbolic t and dx is a sin hyperbolic t, and I can write t as, and if I integrate it, I will get integration of dx is x, okay, by a, then this is integral of sin hyperbolic t is cos hyperbolic, so I take it inverse. So t is equal to cos hyperbolic inverse x by a. So now I can change the limit from here to here. So now here I substitute this. This is your sin hyperbolic ht, and from this dx I get this another sin, so sin square t dt from here, and you have this a from here and another a from this derivative, so a square, and using this cos hyperbolic phi into sin hyperbolic phi is equal to 2 sin, like sin 2 theta is 2 sin theta cos theta. Is similarly here also you can use similar thing, and this sin hyperbolic square can be expressed as this. So if I get here in terms of sin hyperbolic, and this, if I take a integral of this, again I will get something sin hyperbolic. So substituting this here, and when you take the integral, this cos hyperbolic will become sin hyperbolic like this one. So this term and this term will get cancelled, only this term will remain. So this is your half of, okay, this minus half phi a square phi, and this is 0. So only this half of a square phi will remain. So this is very simple. So here also I say that this angle phi is twice the area, like here this angle theta is twice the area. So the angle subtended by this area is half of phi, and here it is half of theta, a is theta by 2. So here I say that for various values of phi we obtain xy. So for various values of phi we can obtain xy, that is x is a cos hyperbolic phi and y is a sin hyperbolic. So for a given x and y, I know where to plot, and I will get a hyperbola. So and here cos is 1, and x square minus y square is as I said, x square, this is the condition. So in circle it was x square plus y square is a square, here x square minus y square is a square. So here this will be always be a. So this is constant. Okay, if I take x square x y here, the difference from here to this difference will be same. Just take an example and do it, or maybe I will do it as we proceed. Okay, now we will discuss hyperbolic trigonometric function which can be expressed in terms of exponential. So in this figure I have shown this hyperbola here, and this angle is your phi, and this base is cos hyperbolic phi, and this opposite side side is sine hyperbolic phi, and this is the point P in terms of this is your x coordinate cos hyperbolic phi, and the y is sine hyperbolic, and this is the hyperbolic equation x square minus y square is equal to 1. And in terms of hyperbolic function, this is cos hyperbolic square phi minus sine hyperbolic square phi is equal to 1. So now how do we find this hyperbolic function in terms of exponential? So here we write area A. This is area A is nothing but area of A plus B, this full triangle, minus this orange region, the area of B. So here we will be using hyperbolic equation, that is x square minus y square is equal to 1. So then y will be, so if I take this y square this side, so y will be square root of x square minus 1. So the area of the triangle, this A plus B, this is base is x and the height is y, which is square root of x square minus 1 from here, minus the area of B. So area of B is integral of y dx, that is y is your square root of x square minus 1 dx, and here in this integral x goes from 1 to x, and this integral you can find it by using any one of this app. This is Symbol Lab or Mathway. This integral, you just put this integral and it will give you this answer. And since here for lower limit 1, so if it is 1, this becomes 0, and then this becomes 0, this log of 1 is 0. So for lower limit 1, it is 0. So this is for the upper limit x. So upper limit minus lower limit. So this is the term. Now this 2 will get cancelled, and you will have twice a, this is 2 here goes here, twice a is log of x plus square root of x square minus 1. So now I can write exponential because this is a natural log, okay, this base e. So e to the power 2a is your x square plus. So you can express this e to the power 2a as x plus y. And similarly, e to the power 2a, I multiply by x minus y, I will get x plus y because of this, and x minus y here. And this x plus y into x minus y is x square minus y square plus xy minus xy will get cancelled. And using this hyperbolic equation, this is x square minus y square is 1, I substitute here and I get e to the power 2a is x minus y is equal to 1. So I can write that e to the power 2a is 1 by x minus y. So here I can write e to the power minus 2a, I bring this up, I take a reciprocal of it, I get e to the power minus 2a as x minus y. It's very interesting to see here this e to the power 2a is x plus y and also 1 by x minus y. So if these two are equal, if x plus y is equal to 1 by x minus y, so I cross multiply, I will get again this hyperbola. So here I have written e to the power 2a into e to the power minus 2a is e to the power 0, that is 1, and that is e to the power 2a I am writing as x plus y into x minus y. So this is what I was saying, you will get the hyperbolic equation x square minus y square is equal to 1. So now by using this e to the power 2a is equal to x plus y and e to the power minus 2a is equal to x minus y, I can add them, and if I add them, this plus y and minus y will get cancelled. So 2x is this e to the power 2a plus e to the power minus 2a, which I have written here, and this 2x, so 2x will come here, so x is x plus. Now since we know that 2a is equal to pi, which we have derived earlier, so I get x is equal to, instead of 2a I write pi here, so I get e to the power minus 5 plus e to the power 5 divided by 2 is, this is your cos hyperbolic pi, because I said that x is equal to cos hyperbolic pi. So similarly for y also you do it, you subtract it, this minus x will get cancelled, this will become plus, so 2y, so this is 2y is this minus this. So y I can express it at e to the power minus 5 minus e to the power 5 by 2 is sine hyperbolic phi. Now we will discuss hyperbolic polar coordinate. So before going to hyperbolic polar coordinate, we know for circular polar coordinate, or you call it a plane polar coordinate, and this is described in terms of r and theta. So this point P is, this base is r cos theta and this opposite side is r sin theta. So this point P is r cos theta comma r sin theta, and this will obey this equation of circle, and I can write similarly cos theta is equal to e to the power I theta, this imaginary theta is coming, e to the power minus I theta by 2, and sin theta is e to the power I theta minus e to the power minus I theta by 2i. So this is unlike your hyperbolic where I is not there. So now here I show a figure for various phi. This phi is 0, this is phi is 1, 1.5, 2. So I take a calculator and find my x and y. X is cos hyperbolic phi and y is sin hyperbolic. So in this blue I have written this hyperbolic value for x and y. This is x and y. So for each of this point here and this point, if you join them, it will be like a hyperbola. And for each of this point, the s, this separation here, x square minus y square, will be 1. So here I have written for this 1 comma 0, this is 1 square minus 0 square is 1, then 1.54 square minus 1.17 square, that is also equal to 1. So similarly for this coordinate, and similarly, and you can also show for this coordinate also, they will all be 1. So this is a property, like in circle the radius don't change, here this quantity is invariant, okay, x square minus y square. So as I said here, this, if you join these dots, you get a hyperbolic hyperbolic, and this is, if it is 45 degree, for x square minus y square is equal to 1, it will be 45 degree, and this is a asymptote. So to understand this hyperbolic polar coordinate further, this is your equation of the hyperbola. This blue line are the hyperbolas, and the phi is, this is the phi, this is the angle phi, it goes like this, and these are the radius from the center. And for each of this hyperbola, this trace r is constant, and for each this dash dotted line, the phi is constant. And here, as I wrote earlier, cos hyperbolic phi is expressed in an exponential form like this, and similarly sin hyperbolic phi, and this is for equation x square by a square minus y square by b square is equal to 1. And if a and b are 1, then it is x square minus y square is equal to 1. Okay, now we will discuss Euclidean and hyperbolic rotation. So let us start with this figure. This is for the Euclidean case. So if you have xy coordinate frame, and if I rotate it by angle theta and make it x prime and y prime, so what I see in this figure, this is angle theta. So sine theta is opposite by hypotenuse, hypotenuse ay. So your opposite side will be ay into sine theta. So these are elementary math. Similarly, this side is your ax cos theta. This is the adjacent side, and this is your opposite side will be your ax sine theta. Because your hypotenuse, this is ax, so sine theta is your opposite by hypotenuse, that is ax. So opposite side will be ax sine theta. And similarly, this length will be your ay cos theta. This is your adjacent side. So now how we express this rotation in Euclidean space? This is point A, which has ax and ay, and this is point B. This is the vector A and B. A is in the black frame and B is in the red rotated frame. So bx and by. So this distance bx prime is nothing but ay sine theta plus ax cos theta, which I have written here. And this distance by prime will be your ay cos theta minus this distance minus ax sine theta. So now one can generalize this x prime is cos theta into x plus sine theta into y, and y prime is minus sine theta into x cos theta into y. And I can write this in a matrix form. This is bx and by prime, that is cos theta sine theta, and this is minus sine theta and this cos theta. So bx prime will be cos theta ax plus sine theta ay, which is here, and by prime will be minus sine theta ax plus cos theta ay, which is written. So by now you may be knowing what is matrix multiplication. You multiply the row with column, the second row with again this column, to get individual component bx prime and by. So now this vector b is r. This is a rotation matrix time this vector a. Okay, this vector is being represented by a column matrix here, and this rotation matrix is this square matrix 2 by 2. So this R is a rotation matrix. So how do we describe similarly the rotation of this Lorentz frame? Here this vector will be tilted towards the, as I said, world line of the light, and this with velocity, this axis will also get rotated towards the world line of the light. This we have explained earlier. This x is beta times ct, and this is for x is equal to vt. This is the particle going with velocity v. It will, this I take it as a time axis, and with the same angle I take the x axis also. So parallel lines with this along this will cut in the x axis. This is our space like line, and parallel to this x axis will cut the time. So it will be the time like line. Okay. So now rotation in Minkowski space, this Lorentz transformation. This is your forward Lorentz transformation in prime frame in terms of the rest frame, and I can write this in a matrix form similar to this. Okay, ct prime is your ct minus beta x, this is the one, and x prime is minus beta times ct plus x, which is here, and gamma is a common factor. So for 3D case, but s prime moving along x axis, I can write this ct prime, x prime, y prime, z prime. These are not moving there. Y prime is equal to y, z prime is equal to z, and this is what I have written here. This equation you will get. Thus we can say the rotation axis corresponds to the direction of relative motion between the two observers. Okay, so it depends on the relative motion. This angle will depend on the, if the velocity is higher, this axis will move towards world line. Similarly, to maintain the simultaneity, this also x prime will also move towards with the same angle. The rotation angle is related to their relative velocity, as I said earlier. Okay, now we discuss based on Lorentz transform hyperbolic coordinate rotation and velocity addition. So here gamma of Lorentz transform gives hyperbola equation. That is, if I write gamma square equal to 1 over 1 minus beta square, this implies I cross cross multiply it here. So this is a x square minus y square equal to 1. So then this becomes hyperbola equation. And we know from hyperbolic relation, this cos hyperbolic square phi minus sine hyperbolic square phi is equal to 1. So I can write this as gamma square and sine hyperbolic square phi as gamma square beta square. So this is what I have written here. And if I take a ratio of this sine hyperbolic square by cos hyperbolic square phi here and take a square root, so I get tan hyperbolic phi as this. So gamma square beta square divided by gamma square is beta square, and I have taken a square root. So this is beta. So from Lorentz transformation, we can also find out this velocity addition. Suppose this is a coordinate with some velocity v1 and this is with velocity v2 with respect to this. Then what is the velocity with respect to the initial? This is phi 3. Okay. So this angle will be added, but velocities will not get added. That we will see here. So here I have shown how with respect to velocity, your this coordinate is rotating. This is the velocity showing here. This is gone in the negative direction. And then when it goes to positive direction, it will go here. So as velocity increases, it will move towards this is your world line. Okay. Now this velocity is decreasing. It is here in the same direction. And now velocity is increasing. It is moving towards. And both the axes are rotating, maintaining this angle constant between this and the world line. So now I write this forward Lorentz transform here. So this is the same written in a matrix form. Now I can substitute this gamma as I had mentioned here as cos hyperbolic phi, and this gamma beta, this minus gamma beta I can write as sine hyperbolic phi. This is also minus sine hyperbolic phi and gamma is cos hyperbolic. So now this is the rotation matrix for the Lorentz transformation for the coordinates. Now I write this angle phi 1 as tan hyperbolic inverse of beta. I take it this side, and so for phi 1 this is beta 1 and for phi 2 is beta 2. So here I get phi 1 plus phi 2 is equal to tan hyperbolic inverse of beta 3, that is equal to phi 3. So then I can write this tan hyperbolic of phi 1 plus phi 2 is equal to tan hyperbolic of phi 3, because phi 1 plus phi 3 is phi 3. Now if I expand this from trigonometric identity, this is tan hyperbolic phi 1 plus tan hyperbolic phi 2 divided by 1 plus this tan hyperbolic phi 1 into tan hyperbolic phi 2, that is equal to tan hyperbolic phi 3. But this tan hyperbolic phi 1 is beta 1, which we have shown here. So beta 1 plus beta 2 divided by 1 plus beta 1 into beta 2, that is equal to beta 3. So if I write beta as v by c, okay, I will get v1 v2 and 1 by c, the common will get cancelled with this v by c. So this c and c will get cancelled. So I had 1 plus v1 times v2 by c square is equal to v3, and this is called the velocity addition in the special theory of relativity. Okay, now we see here some visualization of hyperbolic traces. So here this particle which are there, it follows the hyperbolic path. So each of these particle move in a constant radius. So as we discussed earlier for the hyperbolic traces, and here I show you how the rotation happens. This axis, this time, and the space axis squeezes as the velocity increases. Unlike in the Euclidean rotation, this shape of this triangle is not changing, but here you can see that it is squeezing as the angle is changing. Now some remarks on geometry of spacetime, that is accessible and inaccessible region. So we have shown that time is relative, length is relative, simultaneity is relative, but there is one measurement that all reference frame observers will agree on, that is space-time interval, which we have shown. So here again let me repeat, this is your space-time interval. So this is like the hyperbola equation, this is x square minus y square, this is constant. Suppose this separation you measure in s prime frame or in s frame, this will be same. And if you take other two coordinates as y and z, then this equation is valid. And we also know for stationary frame clock at rest, that is the clock is not moving, this delta x, delta y, delta z is 0, then what you get is a proper time. So the proper time is delta tau is delta s by c. Suppose these are 0, then this is a proper time, take the square root, so that will be delta tau will be delta s by c, where delta s is a real as long as v is less than c, and so is on a time lag trajectory in the space. So I've discussed what is time lag trajectory earlier, so let us repeat what it is. So the space time of a special relativity referred to as a Minkowski space, and here I've shown this is your world line and this is the cone made by the world line. Okay, this is the past, this is now, and this is the future. And here we know that this ct is equal to x, this is the time axis, so this is 45 degree, and for this region here x will be always less than the ct, and here in this white region x will be greater than ct. So this region is accessible because if x is less than ct, v is less than c, which is allowed, but in this region your v has to be greater than c, which is not possible. So this is called the time lag region because it is closer to this time axis, and this is called the space-like region. So one can say that if beta is less than 1, that is if v by c is less than 1, that is v is less than c, then s square is greater than 0. This is delta s, this quantity is greater than 0. But if v by c is 1, that is v equal to c, then this s, the space-time interval is 0 here. It is called light-like. But if beta is greater than 1, that is v greater than c, then s square is less than 0. And then s square is less than 0, and it is called space-like. So this is called a space-like region, and this is called the time-like region. So here any two event in space-time can either be time-like, that is causality holds, or space-like where it violates the causality, or light-like, only communicable by light for s square is equal to 0. So this line here will be light-like. So to repeat again, this is your time axis and x-axis. This is your hyperbolic path, and this dots are all having different speeds, so they are having different frame s prime. This is your s double prime, s triple prime, and so on. And here I have written that delta s square here, or delta s prime square, these all have the same separation, that is equal to 1. And here this hyperbola is open in the x-axis, and again similar thing, proper time is delta tau is equal to delta s by c, and similarly delta s square is equal to delta s prime square. So this is the separation delta s as we have shown here. The space-time interval becomes just a distance. So here I would like to mention that distance in space-time in Minkowski can be negative or even 0, and hence is very different from the notion of distance in Euclidean space. And second point, the magnitude of space-time interval is not easy to interpret. The two events can be separated in time but not in space, or in space but not in time, such that delta s square for these two events are the same. So it is difficult to interpret this space-time interval, and it can be positive, it can be negative, and this separation is in space or in time because you have mixed this space and time coordinate together in the Minkowski space. Okay, now we will discuss some relativistic dynamic. Here I have shown this is your time axis and this is your position axis, and this time axis from henceforth when we discuss four vector from the next slide, I call time axis as x0, x axis as x1, y as x2, and z as x3. Here a particle is moving, and you can see here it's moving with different velocity, so your axis will change, and depending on the speed, if it is going higher speed, then because of time dilation there will be at a further separation, and if it is stationary, then in space it is stationary, so or it is moving very slowly, so these points will come near. So here, not to miss any point, I have written here that tick spacing as measured by the coordinate time x0 varies depending on the instantaneous velocity of the particle. Okay, so this tick spacing will depend on the instantaneous velocity of particle. When the particle is nearly at rest in the chosen reference frame, then the proper time clock runs at nearly the same rate as the coordinate time clock. Okay, so both your this clock coordinate and the moving, they will run at the same rate because they are at rest. But when the particle is moving fast, then its proper time clock runs more slowly than the coordinate time clocks due to time dilation. A curved whirl line is like a series of instantaneous inertial frames, and this we will show it when we discuss Rindler's accelerated frame of reference. Now we introduce four vectors. What is four vector? You have position four vector is a vector that has four components, 3 for space and 1 for time, and it points from the origin. So here I have written here as this is your x0, this is your time component x1, x2, this x, y, and z, and this was introduced by Minkowski. So here he mixed this time and space together and made it four-dimensional. So now we are going to four-dimensional space-time, and Minkowski introduced this time in an imaginary coordinate, and this vector can be written in terms of this basis et, ex, ey. These are the bases and these are the component of the vector, and this et is like this I here, and this distance or separation s square in our Euclidean, in a Pythagorean way, we write s is equal to square root of x square plus y square plus z square for a given vector. But here we have this imaginary thing, so I write as I square become minus, this is ct square plus x square plus y square plus z square. So I can write this s square as like this et x y z, and this is the matrix. So first you multiply these two matrix, so you will get minus ct x y and z, and then we know this basis vector only et dot et or ex dot ex, ey dot ey, or ez dot ez. In a normal Euclidean you take it as 1, but here you take this et dot et as minus 1 because of this imaginary sign. So now when you multiply this quantity with minus ct plus x plus y plus z, and considering this multiplication of this basis vector, you can get in this form. So this is your Minkowski metric tensor matrix. Thus, the length of position 4 vector is called the spacetime interval and is the same for all observers. So whether it is with respect to moving coordinate system or stationary, this separation will be same. That is, s square will be equal to s prime square. If I make this y as y prime, z prime, ct prime, so s square will be s prime square. So as I said earlier, note that here this is your basis vector and they are not changing because basis vectors are the thing which do not change. Only this component change, x, y and z in any given coordinate system. So that's why it is 0. And here, as I said here, that this basis vector, if you take a dot product, it is -1, and e1 dot e1 and e2 dot e2 and e3 dot e3 is equal to 1. And since they are all orthogonal, the cross terms will be 0. So similarly, Lorentz transform basis will be, so this is very similar to your Lorentz transform which we discussed earlier. This is your t prime is gamma time t minus beta x, and here your x prime is gamma time beta t minus x. So here also in the prime frame, this et prime dot et prime is -1 and ex prime dot ex prime will be equal to 1. Now we will introduce velocity 4 vector. So velocity 4 vector is the rate of change of its position 4 vector. This is the position 4 vector with respect to proper time, and proper time is measured by a clock fastened to the particle moving along the world line in 4-dimensional space-time. So proper time is the clock which moves along with the frame, which means that clock is at rest in the frame. So this velocity 4 vector will be ds. S is the position 4 vector divided by d tau, and this s we know it is I c t x y z. So c is constant, so I take a dt by d tau, and this will be your dx k. Okay, this is your x. K is going from 1 to 3. This is 0, x naught, this is x1, x2, x3, and I can do this chain rule. I can take any function of t and tau. So df by d tau I can write as df by dt into dt by d tau. So this is what I have written here, and we know, we have seen earlier that dt by d tau is gamma. So this will be ic times gamma, and here this will be velocity in 3-dimensional, this vk into gamma. So this I call u naught, and this I call it uk, k going from 1 to 3. So this is the velocity 4 vector, and this velocity 4 vector is very similar to this s square, which is invariant, as I said, in any frame. Here also this will be invariant. So u dot u is nothing but u naught square plus uk square. Okay, because u naught, again you see this is your u naught I times, so this is something like I square is minus, so this negative is been taken care. This is your x square and this is your minus. Because of this minus minus it becomes plus here. So if we put this ic gamma in u naught and this is your uk is this, so we get again gamma square. I take common, I get minus c square plus vk square. So if I take this minus c square outside, okay, I will get this as 1 minus v square by c square. So 1 minus v square by c square is 1 minus beta square, and that is equal to reciprocal of 1 by gamma square. So gamma square cancel, and this minus c square which I have taken out is here. So similarly, this velocity 4 vector is invariant under Lorentz transform, that is u prime dot u prime is also equal to minus c square. Now we will discuss momentum 4 vector. So momentum 4 vector is, this is your rest mass m naught, we call it as a rest mass, m naught time this 4 velocity vector. So this velocity is ds by d tau. So I can write again as ic dt by d tau, and similarly your derivative with respect to xk, this is your position, so xk by d tau. So I do chain rule, this dt and dt by d tau, because this dt you can cancel, it becomes dxk by d tau. So here I can write this 4 momentum vector p as p naught and pk, where p naught is ic, this is dt by d tau is gamma, so it is I m naught c times gamma, and here this is m naught times vk times gamma. So here I can write p dot p as p square, because to show whether it is invariant. So I get, this is p naught square plus pk square, what we did earlier. So this is your p naught is this I m naught c gamma square plus m naught vk gamma square. So here I take m naught c square comma and gamma square, I keep it here, and so I get 1 minus this is vk, and because I have taken c square common, I have to divide by c square here. So this is beta, so 1 minus beta square, so it is nothing but reciprocal of the gamma square. So gamma square and gamma square will get cancelled. So I have this dot product of momentum 4 vector vector also give rise to this constant number. So this is invariant if it is p prime dot p prime will also is invariant for the four-vector. So is invariant under Lorentz transform. Now since p naught is your I m naught c gamma, which I have written here. So this gamma I write as 1 by square root of 1 minus bk by c the whole square. So this becomes this quantity to the power minus half, and if I do the Taylor expansion, I'll get 1 plus half of vk by c the whole square. So this in the numerator, this c and this c will get cancelled. So I will have this 1 by c I have taken common here. So this m naught c will become m naught c square, because this c and this get cancelled. I get this term, and this half of m naught because of this, and m naught by vk by c square. So this c and this c will get cancelled. So 1 c I have taken it out. So this is the like a kinetic energy term. So this is the rest energy, and this is your kinetic energy. So I have written total energy as E. So now if I equate this I by C to this, because I have got this quantity from here, so E will be your, so this E will be your m naught, this C will go, this is m naught C square, and this is gamma. So E is m naught C square gamma, and this m naught into gamma I can call it a relativistic mass. So energy is nothing but relativistic mass m into C square. So one obtained this Einstein's famous equation from this momentum four-vector. So here I have written this m is nothing but m naught into gamma. This is nothing but m naught by 1 minus v square by 6. And here m is always, because gamma is greater than 1, so m by m naught is greater than 1. So m is always greater than m naught. So this is the rest mass, and this is the mass which is moving. So it includes the rest mass and the kinetic energy. So here as v tends to c, so 1 minus almost 1, this will be a very small number. So as v tends to c, mass this m will tend to infinity. It means that mass can never be accelerated to a speed of the light or greater. Thus for low speed v, because here we have taken the assumption that v is less than c for this expansion, E is equal to m naught c square plus kinetic energy. And so the kinetic energy, this E is given from here, minus m naught, this m naught c square I'm taking it to the left hand side, and this I take m, this becomes mc square, because m naught into gamma is mc square minus m naught into c square. So this kinetic energy is nothing but difference in the mass, the relativistic mass minus the rest mass, m minus m naught times c square. So this was also discussed by Einstein when we were discussing the paper. Okay, this kinetic energy is the difference in the mass. Now this momentum four vector I can write in a vector form like this, I e c by p. Okay, here you are writing p naught is I e by c, this is your p naught, and this is your momentum p. So p dot p is p square. So I can write as I, this vector, if I multiply, I will get IEC square plus p square. Okay, so you have to do row and column, and you will get this. And also p square is what we have found here is m naught square c square, and from this equation I can get, this is I into I, this I square is minus 1, I take it to left hand side, and this p square is minus m naught c square. So c square it becomes c to the power 4, and this c square which I am taken it in the left hand side, this c square will come here, p square into c square. So from this equation I can get this equation. So here we can see if this rest mass is 0, m naught is 0, then that is for the photon, energy is nothing but p times c. Now if this p square is m square v square, because p is mv, and I can write as m naught square gamma square, because m is m naught into gamma v square, and I can write this as m naught square, this is v by c, c square and this c square cancel, so m naught to v square I can write this way, and here I can write gamma square as 1 minus v by c the whole square. So if I take this on this side and p square I get to the right hand side to the denominator, I get this equation m naught c square by p square v by c the whole square. So then again I take minus v by c the whole square to the right hand side, I will get, and taking this v by c the whole square common, I will get 1 plus m naught times c divided by p the whole square, this one, and similarly you will get this v by c the whole square as 1 divided by m naught, this quantity I write it here. So from this expression one can see that if m naught square is greater than 0, if this is greater than 0, then this quantity is less than 1, so one can say that v is less than c. But if m naught square is 0, then v is equal to c. So this is for the case of photon, and if this quantity m naught is negative, then this will be less than 1, this denominator. So 1 divided by less than 1 will be greater than 1. So here it means that v is greater than c. So this is in the inaccessible inaccessible region which we have discussed. But even if it happens, such particle is called tachyon. We will not discuss this here. And these have many questions, so we will not discuss here. And this particle slows down to approach the velocity. So it is, since it is greater than the velocity of light, this particle, to approach the velocity of light, it has to slow down. And if m naught is equal to 0, then as I have said earlier, that E is equal to Pc. And here this momentum of light I can write from quantum mechanics h by lambda, and this is nothing but h frequency times c. So your energy E is nothing but h times frequency. This is from the quantum mechanics. Now we will show something interesting, that suppose this is a momentum p1 and it is written like this. This is your time basis vector. This is your spatial basis vector a e t plus, and now I reverse this direction here as minus b here, and this one, so if I add this and this, I will get 2a times basis vector et here, because these two get cancelled. But this is not true for the momentum 4 vector. So why this is not true, we'll see here. So if p1 is your this and p2 is your a et minus beta ex unit vector, then p3 is 2a e3, which we have seen here. But if you do like this, then p1 plus p2, then this p1 becomes a square minus b square square root of b. So now this is in Minkowski space. I have to write this separation or a distance a square minus b square, as we have discussed so far, unlike in the Pythagorean way where this p1 is square root of a square plus b square, and then this plus p2 I can write at a square minus of minus b square. So I get here, this becomes plus, so I get twice square root of a minus b square. So here we write this m1c and m2c is not equal to p3, because this p3 is your m3c, and this p3, the distance is, this is 2a, so 2a square, the spatial coordinate is not there, so I just simply write this. And so this quantity is not equal to this quantity, that is a square minus b square is not equal to a. So if you consider this momentum separately, you don't conserve the momentum here. So momentum and rest masses are not conserved in relativity. But if you take it as a whole, that is p1 plus p2 dot p1 plus p2, then so I know here now p1 plus p2 is nothing but twice of a et, so I will get 4a square, only the temporal part, and similarly here the 4a square square root of that, and this p3 dot p3 is your 2a, so square root of 4a square, only this term is there. So now this is valid. So now one can say this momentum 4 vector, that is a dot product of p dot p, is a conserved along with space-time invariance. So now this p3 dot p3 and this is same, so as a whole, and similarly the velocity 4 vector, that is u dot u, is also space-time invariant. Now we will discuss acceleration 4 vector. So similarly acceleration is d square s by d tau square, and ds by d tau is your u, so I can write also this du, this is your velocity, du by d tau, this is your time. So as we know that acceleration is rate of change of velocity, so here I have written this is a 4 velocity vector, and this velocity, as we have seen earlier, that is c times t derivative of dt by d tau will give you gamma, so gamma comes out. So similarly for all, this is du by d tau will be du by dt into dt by d tau, so this gamma will also come out, similarly for these two. So this is a expression for 4 vector acceleration with the condition that et dot et is equal to minus 1, as we said earlier, and ex dot ex and others are 1, but cross dot product of the basis vector is 0. So now I do the derivative of parts, that is d gamma by d tau, I write it like this I keep it constant, and then I take derivative of this quantity, this gamma I take it out here, and this, when I take a derivative, I will get this as acceleration. This is your det by d tau, this is a constant, so this will become 0. So now you will have this 3-dimensional acceleration, and all this dux by d tau I can write similarly du by dt and dt by d tau, and this dt by d tau will become gamma. So you please take pen and paper and try to get this. It's very simple. So here I have written that derivative with respect to c, this one is 0 because c and e's are constant. Now if you simplify this, dt by d tau, as I said, is gamma. So gamma times this quantity, see the previous slide, that is nothing but the 4 velocity vector plus this gamma square times this a acceleration. And this acceleration is a 3-dimensional acceleration, not the same. And now this d gamma by dt, one can write as d by d tau. This is your gamma 1 by square root of 1 minus u square. This square root I can take in the numerator, it become minus half. So this is minus half, minus 1 is minus 3 by 2. And now derivative of this quantity. And this derivative will give you, this is 2u du by dt, that is du by dt will be acceleration, so a dot u by c. So this d gamma by dt is nothing but this. So I substitute here, I will get this as minus here, so I write this quantity as minus a dot u c square times u and r square is here. So now I can write this in terms of a matrix. This is gamma square here. This is your 3-dimensional only ax, ay, az. There is no 4-dimensional here, because if it's the fourth is there, then this will become this a, but this is 0. And then you have this quantity here, and this is your u. This is c gamma ux gamma, which we have seen for the 4 velocity vector here. So that I can write gamma square, I take it common, and I can write. So this acceleration 4 vector can be written in this form. So this is a bit complicated than the earlier two, which you could have written in one column like this. This is the velocity, and the spatial will be c times t. There's no gamma. Gamma comes because you are taking derivative of t with respect to tau. So for position 4 vector will be c tau, then x, y, z. So from this we see that a is not necessarily parallel to a, because you have a dot product in the spatial dimension. So now, since maybe you are a bit confused, so let us recapitulate again these 4 vectors. This is a position vector, we have written like this, and s square separation square or distance square is written like this, which is invariant in all inertial frame of reference. And with this condition, et dot et is minus 1, and other ex dot ex and ey dot ey, ez dot ez is plus 1. And s I can write in vectorial form like this, x naught x1, okay, x naught is ct. And similarly, your velocity is nothing but dx naught, this derivative with respect to tau. So if I take this dt, as I said earlier, this dt by d tau is gamma, so I have gamma. So these are the component of the 4 vector velocity, and this is the momentum 4 vector, and these are the component. So this is a time component e by c, and these are the spatial. And as we discussed in the last slide, this is the acceleration and this is the thing. Similarly, you can define force 4 vector, and you take derivative of momentum with respect to tau, and here these are the spatial coordinate. And the interesting thing is that the time component of the 4 force, that is, this is the time component, is the power, that is rate of change of energy, and f is dp by d tau, and I can write this as m into this velocity for vector velocity, and this m is constant if I take it. So this is your mass into acceleration. So this 4 vector obeys the Newton law. So in relativity, force is a 4 vector, that is 4-dimensional. Now let us also recapitulate Lorentz transformation. This is a reverse transformation because of the plus sign here. This is for any vector. So for Lorentz transform, for the position is, we have seen this gamma x naught, this is a time, and b times x1. And for this also, this is your time, beta times ct. Okay, x naught is ct here, and this is x1 is x. So here this is the Lorentz transformation. Here x naught is ct, which I have said earlier. And similarly for Lorentz transformation for this velocity, and here also along the x direction, like what you have done here, because y and z is constant. So here also you have same thing, and here u naught is dx naught by deta, that is gamma c, which we have written as in the 4 vector term, and u1 2 3 is gamma times v 1 2 3, we have written in 4 vector the spatial coordinate. And momentum Lorentz transform, again in the direction of x axis, you have very similar thing. Here you have p naught and p1, this is your time component, and this is your spatial, and this is also your spatial component. And here p naught will be your e by c, that is gamma m naught c square by c, okay, e by c, and p1 2 3 is just nothing but m into v velocity, okay, this momentum. Now for this Lorentz transform for acceleration is also very similar, and here this a naught is nothing but your minus gamma square a dot v, this is your temporal part, and your spatial parts are this. Okay, now we talk about momentarily co-moving inertial frame, or sometimes it is called instantaneous or momentary inertial frame. So here I have shown a figure. This is your stationary frame called this S frame, and this is the world line of the accelerated particle. And here I have shown that this is the basis vector for the stationary frame. This is your spatial basis vector, that is Ex, and this is Et in this direction. And similarly, I have drawn for the moving frame in red arrows, and we have taken velocity as a tangent to this curve. So I have taken this time in this direction, in the direction of the velocity, and we will show that this Ex, the spatial coordinate, the acceleration is perpendicular. This is the velocity, so acceleration is perpendicular to the velocity. We'll show it, and along this basis vector you have the acceleration, and you can see that acceleration for the stationary frame, I have, this is, say this is acceleration, you can write as this is the component in the Et direction and B is the component in the Ex direction. So I write acceleration as a sum of these two components, whereas since acceleration is along this Ex S triple prime frame, so acceleration is in this direction, so I can only one component is there, so I write alpha times Ex triple prime. So I have these three frames here I have shown. This is your S triple prime frame, this is your S double prime frame, and this is your S prime frame. At each point, at momentarily, it has an inertial frame. That means at each point you can consider the velocity to be constant. And interesting thing, you see that for this, for stationary frame, these components are varying, but whereas in the moving frame this component is not changing. This is alpha, which we will see it. So here velocity is parallel and tangent to the world line, and I represent by this basis vector Et. So this is tangent to this world line and parallel locally, and in that frame one can think that they are stationary in space, because we are considering this momentarily, these are all inertial frames. So since we are considering it is stationary in space, I can write the velocity as only this time component, and the component in the spatial basis vector, they are 0. So here we will show that A is orthogonal to U, and the observer in the frame has purely spatial acceleration. That means it has only the spatial component but not the time component. Time component is 0 here. And since they are orthogonal, we will show that U dot A is equal to 0, because if I take a proper derivative of velocity U dot U, I can differentiate by parts, and I will get there twice of U dot A. Okay, this du by d tau is acceleration. I can write as 4 acceleration vector here, and this is also 4 velocity vector. But I know we have seen earlier that U dot U is minus c square, because these are invariant and these are constant term. So derivative with respect to tau, this will be 0 because these are constant. So thus this 2 U dot A is 0. So it implies that U dot A, that is they are orthogonal. U dot A is 0. So for stationary frame, the component of A are changing. For stationary frame, this A and B, this is 0 and B, because A is only in this direction. This doesn't have this component. And here again, this A is in this direction, so it is in the negative time component and positive spatial component B. But for the accelerated frame, these are all in the spatial direction with same component. So I write for stationary frame, components of A are changing, whereas component of A are not changing in the MCIF. So they are not changing, it's all alpha. So this is the case for constant proper acceleration, and this is also called as Rindler's frame. Now let us again draw this figure which we have shown earlier. Let us recapitulate what we have studied so far. That this is your hyperbolic path or constant accelerated path, and these are the radius. This is c square by alpha prime. This is for, and this is for another radius. These are all different radius where r is constant, which we have shown earlier. And here we see these are the phi. This is phi is greater than 0. We will find out what is the value of phi with respect to tau in maybe next slide. And here phi is greater than 0, and here phi, the angle is 0, and here phi is negative, less than 0. So these all we have discussed earlier. This is a hyperbolic equation. X square minus y square is c square by alpha. This is your first radius, and when this acceleration changes, you will have another set of, because alpha is constant here in this blue line, then if alpha changes, we will have another hyperbolic path, which I have shown here. This is for alpha double prime, and so on. So now in the instantaneous rest system, gamma is equal to 1 because v is 0 in the rest system. So this gamma is 1 over square root of 1 minus v square by c square. So this v square by c square is 0. So 1 over square root of 1 is 1. So gamma is 1. So the proper acceleration, this is alpha mu, I write it here, and mu goes from 0, 1, 2 and 3. 0 is for the time, and 1, 2 and 3 are for the spatial. So here I write acceleration is the proper time derivative of this velocity. This is the velocity 4 vector again, and since this is with respect to tau, proper time. Again, as I said, using chain rule, I can write this derivative with respect to time and then dt by d tau, and dt by d tau is gamma. So I keep this gamma common and I can write this mu naught will be your c times gamma, and since gamma depends on the velocity, this will depend on time, so I write d gamma by dt. And similarly for the spatial component, I can write this as gamma v, which we have seen earlier. So I write derivative with respect to time, this gamma v. So this is nothing but your acceleration, the time component of the acceleration, and this is the spatial component, and this is the three-dimensional acceleration. So here I say this alpha is a Newtonian relative 3D acceleration. So now I can write proper acceleration in a Rindler space, and mu goes from 0, 1, 2 and 3, and since I have taken gamma equal to 1 for a instantaneous rest system, so this quantity will go to 0 because this gamma is 1, and similarly this dv by dt, this gamma is 1, so I can call this as acceleration because we know this is rate of change of velocity is acceleration. And if I take this acceleration as constant, so let us take constant, so I have this acceleration is this quantity here, and now I introduce this Lorentz factor, so this is v times gamma. Gamma is your 1 by 1 minus v square by c square square root. Okay, this is minus because you have got it up. Now I take this dt to this side and integrate it, and I get alpha t, and this derivative, this one, if I take integral of dx, I will get x. So that is what I have written here. It is the same thing. Now I square it and rearrange it, and then again take a square root. I will get this vt is equal to alpha t by. So please try it out using pen and paper. So now I know that v velocity is nothing but dx by dt. So I can integrate this one, and I will get here xt because integral of xt dx will be xt. And I take this alpha out, and again right hand side also you integrate, and you can do by substitution, but I will not do it here. So as I had told that you can use those math application which I had mentioned earlier, so you can find this as a solution. So again squaring it and rearranging, you will get this equation. So this is like x square minus y square is some constant. This is like a hyperbolic equation. So from here we can see that if you take instantaneous rest system, that at each point it is momentarily at rest or momentarily they are at inertial frame, then you get this, and this distance from origin to here is your c square by alpha square. So this is your radius square. And so from here you can see that as t tends to infinity, so this quantity is very large and this is square root. So you have alpha t and alpha t get cancelled, and this is square root and this square will get cancelled. That means vt tends to c, and for small value of t, that if this value is very small, then vt is proportional to alpha t. So here I can say that at t equal to 0, it is c square by alpha. So here it will be c square by alpha. This is at time t, this is y axis is time. At t equal to 0 you have this, and for small t, you see from here you will get this c square by alpha here, and this is, you do a Taylor expansion, and you, when you multiply this, you will get alpha t square by 2, and you neglect the higher order term of the expansion. While for large t, when t is very large, then you can neglect this one. You have alpha t, and alpha get cancelled, c get cancelled, so it is x is equal to ct. That is x of t tends to ct as t tends to plus or minus infinity. This motion is represented by a hyperbola. And now in the convention of plus minus minus, that is your time component, you take plus. So some people take minus plus plus plus, or here if you take plus and the spatial component as negative, then you can show this dot product of acceleration four-vector is nothing but, I am using this convention, so I am taking this as plus and the spatial component as negative, because these are our hyperbola. So instead of plus it becomes minus here because of this condition. So this one is nothing but du naught, this is a time component with respect to tau square, and this alpha, this is in x direction, so this will be du1 by d tau square. Then I transform this derivative with respect to this time. So we have seen this earlier also, this will become gamma square because du by dt by d tau, dt by d tau is gamma, so gamma square will come out. So this is d mu naught by dt minus, for similarly for this one also, this gamma square is common, and this we have shown earlier as minus alpha square, which you can see from here also. This is your acceleration. This negative sign is here. So this is a acceleration. So this is this Newtonian relative 3D acceleration. So here again I reproduce the previous figure here, and now we want to derive this phi. What is phi? How it is related to proper time tau. So this is how it is related. So let us prove this. So considering moving in x direction, and we have already earlier said that this rate of change of basis vector, they are constant. So this will be 0. Now we can write this 4 vector acceleration A as a proper time derivative of 4 vector velocity. And this 4 vector velocity I can write like this, as we have written earlier. This gamma times, this is your time component, and this is a special component. This is with respect to proper time. So now I can write this. This is a time component. I can write as ut. This is your basis vector in the time component, and similarly here I can write the spatial component of this 4 vector velocity here, and this is the spatial basis. So I can write this vector A as this time component with basis vector et plus ax times ex. So this is a general convention which I have used it here. So using this convention I can write this dot product of this 4 vector acceleration as, since these are, we know that these are hyperbolic, so I have to take this difference, and this definition we have referred many times, so I don't want to repeat the same thing again. So this velocity time derivative or proper time derivative is this square minus this square, and that is equal to minus alpha square, which we have shown it earlier also. And since this is constant, we say that it is valid for all inertial frame and even in prime frame, because this is a constant. And similarly velocity dot product or 4 vector velocity dot product, again I can write similarly here. This is a time component, this is a spatial component, and that is equal to c square, which we have shown earlier. So I can take the ratio of c square by alpha square like this, and I can write this c square is here. This is the thing which I have substitute here, and alpha square I have written here. So here you can very easily see this is negative, so I have to flip it. So I will substitute this ut by c by alpha ax because I want the negative sign, and similarly ux is equal to c by alpha times this time component of a here. So I have this common, c by alpha square will be common, and then this at minus ax square will cancel with this. So I will have c square by alpha square negative. So this is the solution which satisfies this equation. I take this one and I can write this alpha, this velocity x component of the velocity by c as acceleration, the time component of acceleration. And we know that this acceleration is the proper time derivative of the time component of this 4 vector velocity. Now I substitute this here instead of this. This is your velocity time component here, and I know this acceleration, the spatial component will be your this dux by d tau. Okay, this is the spatial component of the velocity. So spatial component of acceleration will be proper time derivative of this spatial component of the velocity. So now I have this double differential here. Now I write this here, and this alpha and c I take it to the left hand side. So I have this double differential of this ux, and this is a very easy differential equation, but anyway you substitute this value, this exponential alpha c by tau, and it will satisfy. You take a double derivative, left hand side you substitute this and take a double derivative, and you will see that they are equal. Or even you can take this e to the power minus alpha c by tau, that will also satisfy this differential equation. And since we have shown earlier that cos hyperbolic phi is nothing but u minus phi plus e to the power plus phi divided by 2, and similarly sine hyperbolic phi is e to the power minus phi minus e to the power phi by 2. So here this phi is nothing but this alpha by c into tau. So here I write this phi is equal to alpha by c into tau. So this phi is, this is the value of phi, and where this alpha is constant for each of these hyperbolic paths. So far what we have learned in special relativity, we have learned that 3-dimensional space, length, delta x, time, delta t, velocity, momentum, simultaneity, and kinetic energy are relative. And we have also seen that in special relativity, velocity of light c is constant, that is, this is the value. And we have also seen this space-time separation because it has a hyperbolic path. It is this ct square minus x square minus y square minus z square. In special relativity, Minkowski 4 vector, this is this position s, then velocity, then momentum, acceleration, and force are invariant in all inertial reference frames. These are all 4 vectors. They are invariant. We have also seen that in all inertial frame, the laws of physics physics are the same. And in special relativity, four velocity and four acceleration are orthogonal to each other. Then constant proper acceleration is constant, that is 4 vector A dot 4 vector A is minus alpha square, which is constant. We have also seen that equation of motions are hyperbola with initial condition, that is proper time equal to 0. This is c square by alpha. This is a spatial only because time is 0. And the 4 vector velocity at tau equal to 0, you have to consider velocity in this time basis vector because we are considering velocity tangential to this hyperbolic path. And the position vector is represented by hyperbolic trigonometric function, that is sine hyperbolic and cos hyperbolic. And this is a phase factor which we have shown that phi is a c by tau. And this is the radius from the center to this. This is c square by a square. So this we have discussed elaborately. And we have shown that in Rindler's horizon, this is your Rindler's horizon. For accelerated observer, the Rindler horizon is located back at L0 is equal to c square by. So this distance is L0. So this Rindler horizon is located at this L0, which is nothing but c square by alpha, where alpha is the S. And we can see that light cannot arrive from behind the Rindler's horizon. The space beyond it appears dark. So what it means that this is a Rindler's horizon, and if I shine the light here, and if the light is here, you will never able to see it. It will never cross here. So beyond horizon, this place will be dark. So if you are in this frame, you cannot communicate here. You will always see this region to be dark. We can also see that if light is sent towards Rindler horizon, it appears frozen in space-time, and this happens because of time dilation to the accelerated observer, and it is similar to the black hole in the flat space-time. So you will see that because of this condition, the light will never pass this horizon because you cannot communicate with this. Okay. So last and finally, we can see that if an observer is accelerating in the positive x direction, so this is your acceleration in the positive x direction. Example, they feel a constant force pushing them in the positive x direction because their accelerating means it appears as if there is a constant force pushing them in the positive x direction. Their Rindler's horizon will appear behind them in the negative x direction. So this appears as if it gives rise to uniform gravitational field, which is the equivalent principle in general relativity. So I think now this is the best point to stop here because we are introducing now this general relativity where we know this acceleration and your gravitational field, they are equivalent, which we will see when we discuss general theory relativity. So I think we will start from this point when we discuss general relativity. So I would like to give an advice to students, those who have gone through this talk up to here, then I think it won't be a bad idea that you mute it and start again from the beginning and write it down those steps. And I'm sure maybe my English may not be so good, or maybe some of the things I might have made mistakes. So they should write it down in pen and paper and solve each steps, and I'm sure at least you will have some hold in this subject. And this will be prerequisite when we discuss general theory relativity. So thank you.